Okay, ideal gases versus real gases. An ideal gas has no attraction between the gas particles, and the particles themselves are so small relative to the whole volume that we can just completely ignore them. At STP, real gases act very much like ideal gases. So here we've got a graph of the molar volume of different gases. So for the ideal gas, 22.41 liters. Chlorine, carbon dioxide, ammonia, nitrogen, helium, hydrogen, we see very similar numbers, right? Helium is even exactly the same. So it's behaving like an ideal gas, meaning it's obeying the ideal gas law. If we get to high pressures or low temperatures, though, we start to see deviation from ideal behavior. So the volume of the gas particles becomes significant at high pressures. So here we have low pressure, and here we have higher pressure. Higher pressure, those particles are getting squeezed closer and closer together. The closer they get, the more the size of the particle matters. So if you took the people from Wyoming and you herded them together and got them into a smaller and smaller place, now eventually you're going to get down to like the elevator where things, the size of the people matters a lot. So higher pressure, particles squished closer together, now the volume of the particle compared to the volume of the whole gas is no longer negligible. They are taking up space. And so the volume that we observe is higher than the volume that we calculate, because the calculation ignores the actual volume of the particles. So here's a graph of that. Molar volume versus pressure. So we've got two gases, the ideal gas and argon, a real gas. So as up here where the pressure is low, these are right on top of each other. As we increase the pressure, we start to see a separation in these two lines. And out here, the volume of argon is definitely larger than the volume of the ideal gas. Because the ideal gas, its particles have no volume, and so you can squeeze those together infinitely. You can't do that with a real gas. So a guy named van der Waals made some adjustments to the ideal gas law to correct for these things. So this is the correction for high pressure. So here the volume is equal to nRT over P, that's the ideal gas law, plus a factor. So this B is the van der Waals constant, or a van der Waals constant. It's going to be different for every gas because all gas molecules of different compounds are different sizes. So that depends on what gas you're looking at, and it's also affected by the number of moles of that gas. So that's always going to make the volume larger. At high temperature, pressure of gases lines up right with the ideal gas law. It's really good. But at low temperatures, we start to see deviation. The pressure then is actually less than what we expect. What happens here is that when the gas is at a lower temperature, it's moving more slowly. And now when those particles run into each other, they actually have a little time to interact. So if you think about these attractive forces being like maybe people meeting each other, right? So if you are just rushing past people on a busy sidewalk, maybe you're in New York Times Square in New York City or something, and everybody's just rushing around. You can bump into people, but you're just on a mission. You have no time to interact with them and realize, ooh, I'm really attracted to this person. Whereas if you were moving very slowly and bumped into them, you might have time to interact and realize, ooh, I kind of like you. And so that would kind of keep you together a little bit before you move on. So at low temperatures, the actual attractive forces that are present between all particles start to come into effect. And so that causes the pressure to be lower than expected. So here we've got a graph of that, looking at the pressure in atmospheres versus temperature. So at high temperature, the pressure of a real gas and an ideal gas are the same. At low temperatures, now the real gas is showing a lower pressure than the ideal gas because xenon atoms are attracted to each other. And when they run into each other slowly, they can stick. Actually, what's better than the people on the sidewalk is people in Velcro suits. So if you're in a Velcro suit, you've seen those Velcro bounce house things where you put on this Velcro suit and you jump and you stick to the wall, right? Kind of crazy. Lots of surface area. And yet the Velcro on your shoe won't stay together, right? But you can stick to a wall, right? It's all about the surface area. If you have things covered in Velcro and they're moving very fast, they've got momentum and they'll just kind of go past each other. The Velcro won't grab very much. But if they're moving more slowly, then the Velcro, it's stickier, it grabs more. And so the particles don't move the way they did before. So that's what's happening with the pressure here. Van der Waals also made an adjustment for this. A is another Van der Waals constant. Again, it's different for every gas. This takes into account the effect of intermolecular attractions. So the pressure is nRT over V minus a term. Now the good news is we don't need to use this, but it's out there in case you did some complicated thing. There could possibly be a homework problem that would make you use this, but I would never give this to you on an exam. Here's when you take both of those corrections and put them into the ideal gas law. PV equals nRT, that's nice and simple and elegant. This is a mess, which is more like real life. And just in case you would ever need them, here are some of the Van der Waals constants for different gases. If we look at pressure, volume over R times temperature for 1 mole of gas. So what should that be, right? PV over RT equals N, right? So if we're doing this for 1 mole of gas, we should just get a straight line here. So here's PV over RT as a function of pressure. So an ideal gas will give you a flat line at 1. Real gases, though, are going to behave differently. So here, helium is a nice straight line, but it's always above. And what this means is that the most important factor causing deviation here is the actual molecular volume. Helium particles have very little attraction for each other. Water molecules have a significant amount of attraction for each other. And so we see the curve for water, it actually goes way down here and comes back up. This is lower, and that tells us that the intermolecular attractions, the stickiness of the particles, is the most important thing. And then some of them, like xenon, the stickiness is a problem at lower pressures, and then the actual size becomes a problem at higher temperatures, higher pressures.